Okay, today this lab is lab 9 and we're gonna finish this model. So today we're going to make we're gonna finish up some things in the fan. Then we are going to create the gluing, which is here. Then we're gonna create the boundary conditions. We're gonna apply the loads. We're gonna apply constraints. Then we'll um, ask for some output from the bushing on the bushings. Then we're gonna run the simulation and get results. Okay, so this is what you're gonna get eventually. You should have those are the gluings between the solid mesh to the 2D shell. Then we have inserted a nylon bar and the forces, and that's the results. So it's okay if you have your results within 10% of mine. That means it's good. Really, that depends on the gluing, how you pick, how much surface you pick, and also you want to check the animation. You want to see this bar is straight and the jaws are coming into the center because we fixed this point here. So there's some couple ways to examine how the model is the model correct or not. And also don't worry about this this piece sticking out. That's exaggerated, and also NX doesn't care about the interference between meshes. Okay, you have to take care of that yourself. All right, so let's turn this off and get straight into our model from last week. So from lab 8, you should have all the joints made. I'm still in the sim, so go to the FEM, and I have to clear this, get back to where it was. I think that's the only mesh we have to make today. Yeah, okay. So from last week, you should have something like this, and also you should not have, you wouldn't see the solid pin here, you would see just the line representing the C bar here. I assigned the material and the cross section, that's why you can see the solid. Okay, so first we want to insert the nylon bar on the tip, and that's very simple. You can first insert a node at the middle, in between of this node and that node. Okay, and make sure when you pick those two nodes, you want to we want to insert between nodes. You want to pick the node on the symmetry plane, and one way is you can turn off the other half. Well, of course, you have to know which half you have. Then you can pick the corner node. And you can leave half on. So this job is a whole thing. I just pick the middle. And this one is an example of if you turn off another half. So I'm gonna pick the corner node, and that's the node you're gonna create for the nylon bar. And you can hit F8, look from this alignment. Okay, that's right on the symmetry plane. So we can say OK. And the nylon bar is built on 3 nodes. One here, one in the center, and the other one on the other jaw. Okay. All right, then so let's see next. That's the 3 nodes. Then oh, I didn't explain here. So you might want ask why you don't need any connection between the C bar and the solid. And if you still remember from the pin joints, if those two elements share the same node, that means they're going to transfer everything, the load, the momentum, the moment. So which is not true for now. If you think about your vice grip is holding a piece of nylon bar, the bar is not welded on your the nose tip. Well, the thing here is ideally or realistically, the C-bar should have some kind of bushing between the C-bar and the solid element. However, the solid element does not have degree of freedom on 4, 5, and 6. So, look from the surface, you would think, okay, the C-bar and the solid, they're sharing a node, and they're welded. But actually not. Actually, the C-bar can rotate on the solid because the solid doesn't have degree of freedom on 4, 5, and 6. So even though we later on we're going to fix constrain the C-bar, the solid will not be fully constrained because they don't have a degree of freedom on 4, 5, and 6. So you can't constrain them this way. That's why we needed a second constraint to prevent this whole thing from rotating. Alright, so here we just go insert element and create a C-bar, and you want a new bar, a new collector, because that's different material and different sections. So C-bar here from the node on the tip and to the center. Then second section you want to make sure it's added to the last C-bar mesh you created. Okay, and then say okay. So they are sharing nodes, but the moments will not be transferred into the solid. Okay. Well, if you want to transfer moments from a bar to solid element, you can get a spider from this bar to grab those nodes here. So this way, you're transferring the moment through actually the translation of two nodes. So one node is going to translate, actually going to rotate with respect to the other node. That's the translation motion in terms of this node. However, if you look at those two nodes, that's going to be a rotation. So there's a couple of ways you can do this. And well, enough for the nylon bar. Then next we're gonna assign the materials and the thickness or the sections for the elements. So we can start from, let's see, from the easiest is the 3D meshes because it only has material. There's no thickness nor sections. So you want to go to your collectors, 3D collectors, double click or right click and edit, and edit again. Then you want to pick material. I have done that already, so it's here. You should go to your material library and find a steel, okay, and pick that for the 3D solid. And actually those two pieces are the same, so you can either pick a material for property solid 2, or you can just use the first property because they're the same. And after you finish this, we're gonna go to the 2D meshes, and all three of them are on different thickness. So the jaw handle, it's big piece, and edit and monkey wrench. Material steel again, and don't change material 4. That's for composites. So the default thickness is 0.1 inch, which is in the table here. Okay, then you can say okay. And by default, you will not see the thickness of a 2D shell. What you can do is you can edit display and let's see, where's the element thickness and offset. So if you enable this, you can actually see the thickness of the shell. and you see cracks here because it's the cylindrical face. They are connected in the middle or at the bottom. I think it's in the middle. Alright, then usually we don't use that, so I'll turn this off just in case you want to see that. Then the link, again, that's a steel. Well, the whole thing is made out of steel, except the nylon bar we're gonna clamp on. So thickness here 1875, and okay. Then grip, which is 0.07 inch. Okay. Then after you assign the thickness and the material for the 2D, we're gonna go to the 1D collectors. Okay, 1D collectors. So for now, all your pins are gonna look like this, aligned, because we haven't assigned a section or the radius of the C bar. Okay. Well, so we're gonna take a look at the collectors. RBE2, as we said before, they don't have physical properties, so you can skip that. Mostly we just assign material to the bars. So the first bar, I'm not sure which one this is. So that's the pin pin connection 1. So this one is 0.115. Yeah, let's take a look at inside. Then you want to define the 4 section and get into 4 section. You would create a new one if you haven't done so. And here, if you create a new one, you would see something like this. And dimension 1 is actually the radius. So gotta be careful. That's the radius, not diameter. Then just keep this on the one you created and close this. You can have, once you click OK, it's gonna show you the solid. So you can do the same for these 2 pins, 2 and 3. Then the screw is the same as those 2 pins. Then the last one is the nylon bar. So nylon bar is here. We just created and we haven't assigned the material and 4 section yet. So the 4 section here, the radius is 0.125. I think I have one of them, should be the last one. If you're not sure, and you can go into edit. The other way is you can use this information. Okay, so information for this section, radius is 125, and there's also a moment of inertia. Sometimes you have to, if you need to do hand calculation, you can just get moment of inertia from here. Okay, so that's the rod 3 for the nylon bar, and material, of course, that's the nylon. And once you click OK, you can see the solid. And I think sometimes people don't like the solid bar. They want to edit the display and change the display section to curves. Okay, so something like this. So it will always be wireframe if you choose curves, even though the whole model is on shaded. Now, there's one advantage is that you can actually see the spiders inside the pins. So, yeah, you have to do it one by one. So, it's just preference, it doesn't matter. Okay, so I'll leave those in solid pins. Okay, so we assign materials, we define the geometry of 2D and 1D meshes. Sometimes you need to check it. And it's kind of a headache to get into all the collectors to see which ones are steel, which ones are nylon and the thickness. So there's ways you can check them, and that's the navigator views. Here is the standard view. We can see the collectors. And if you right click on the name, we have a material view and a physical property view. So let's take a look at material view. If you change that to material view, expand this, you can see we have 3 categories for the whole model. And no material that's should be the RBE2s. And also the polygon. Polygon don't have material. Okay, and we can turn everything off. Then you can turn the nylon on, which is only the bar. So that's good. And the steel, a lot of stuff. We can get into the steel and take a look. The 3 2D meshes and 2 solid jaws. Then those 3 pins plus 1 screw. So that's all for our model. And sometimes you gotta be careful, no material. Now if you see C-bar 2D mesh here, you have to assign material for them because they should not appear here. Then the next view is a physical property view. So here, I guess if you have a large model, you would actually write down what are the materials are, what are the physical properties. So P shell 1, that's they're different because of the thickness difference in here. You can take a look by right click on information. So P shell 1 is your 0.1 thickness. This material is steel, which is this one. Okay, so you can check the meshes under those different categories. Okay, so as you can see, P bar 3, those 2 pins, because they're the same in diameter or radius. And then we have P bushing 4, that's the 3 pin joints. Okay, 1, 2, 3 here. Then the property bushing 5, it's the ball joint. Then the last bar is the nylon bar. No physical properties, that's the RBE2s. They don't have any material thickness, stiffness. Then we can go back to standard view. Okay, so that's kind of one check for your model before you go to the sim. Then okay, so now we switch to the sim. Yeah, let's take a look. Okay, let me delete the gluing first. Also the regions, the group. So this is what you should get when you get into the sim. Okay, just meshes. Probably have different colors. Alright, now here we're gonna do the first thing is we're gonna glue 2 pieces together. We're gonna glue the handle to the jaw. The whole piece is called jaw handle, right? But they are in 2 different pieces of meshes, 2D and 3D. And so now we're gonna glue them together. That's similar to a rigid connection, and it's also similar to RBE2 in my opinion. And gluing will transfer the loads, the forces, and moments continuously. So regardless of the type of your mesh, and so that's a good thing about it. Then also take a look at the gluing. For gluing, we'll glue 2 regions together. They call that region. So the gluing is in here. It's one of the simulation object. And we have different types of gluing. We have surface to surface. So today we're gonna use edge to surface, because that's the 2D edge to the 3D as a surface on the 3D. So edge to surface gluing, we have edge region and surface region. So you would probably think, okay, we have this U-shaped edge. We're gonna glue that to the solid, right? So can we just pick 3 edges of the U shape and then the surface region we pick 3 surfaces on the jaw. Well, that's not recommended because the regions, you don't want that to go over a sharp corner, which is here you have a 90-degree corner. You don't want that. It's probably okay if you have a slightly curved edge, but this is totally different direction, so you don't want that. So you actually want to separate these three edges into three gluing. So here you have to edge the top first, then the back, the bottom. And the region we can create now. Okay, you can create this regions in the gluing command on the fly by clicking this button. And it'll create a region. And personally, I prefer just create all the regions before you get into gluing. So what I'm gonna do is here the regions is actually in this folder. You can right click and create a new region. That's the same window you can activate from the gluing window. Alright, so we can define two types of regions. We can first define the edge region. And here you need a little bit help from hiding things. So you want to hide the 3D meshes so you can see the edges. So edge, we're gonna say that's the top, or rather, yeah, that's the top, Z positive. So this is the top edge, and that's a long edge. We have to use some tricks. So feature element edge, then pick this edge, it'll pick the top edge, and you can rename this. Let's say that's the top, and don't have to change anything, just apply. Then the bottom, feature element edge, the bottom edge, let's say the bottom. Then we have a vertical edge, whichever you like to call it. Call that back edge. And okay. So now we have three regions in this folder. Okay, you can click them and take a look. Then you can right click, create new surface regions. And now we have to turn off the 2D, show the 3D. Okay. So the top tangent face, that's probably we can do that. That's face for the polygons. We need element faces. So feature angle element faces. The top, we're gonna pick the whole face. And the gluing, how gluing works is that you can define a distance. Say within this distance, you're gonna glue everything within this distance. So it doesn't matter really, you pick a large surface or small surface, as long as you define the right distance. So that's the top on the jaw region. And here's something, the surface, you want the top surface or the bottom surface. So for a 3D texture, it's always the outside surface is the top. For 2D meshes, you're gonna be careful if you're picking up 2D meshes as your region, because 2D they look the same from both sides, right? So you have to check their 2D normal to see which one is the top. The direction, the normal points is the top and the other side is the bottom. And you can check that in the FEM. And it's irrelevant in this class because we don't pick 2D surface regions. Alright, so that's for the top region. Then we have a bottom region. Again, that's the feature element, angle element face. That'll be the bottom. And okay. Then for here, that's actually from the edge, okay, to this fillet or the edge blend. So this face is probably hard to pick. You can take a look where it intersects. It's about here. So as long as we pick some elements near this region, that's gonna be enough. So let's try pick this. Apparently this feature element edge, that's too the tolerance is too big. So I'm gonna deselect to Shift and click. Then change the angle of this feature element edge tool. Let's try 10 degrees. It's probably still too big. So that looks okay. I'll just pick something here. Now that's too much. So maybe a little smaller, 5 degrees. Keep picking. And you see a line that's highlighted. That means you accidentally clicked the element behind those things, which is the bottom. So you want to deselect that. Yeah, that looks good already. So that's the back. Okay. And then, all right. Now we have. Oh, by the way, I think you cannot have the same name as the other region. So I'll say that's the jaw top. Yeah, that's the. Let's try rename. Jaw bottom. This is jaw back. Okay, so 6 regions, and I'm going to glue them together. And let's go to edge to surface gluing, edge region, the top, and well, we can show everything now just to see to the jaw top. So it'll glue those two together, and now you can see there's a search distance. So it'll glue everything within this tolerance. You don't have to change that because our model is actually touching each other. So we can leave this as default and apply. And once you apply, it's going to show you the indication, graphical indication. It's pretty messy. Well, we can keep doing this for the bottom and for the back. Apply. Then if you go to the simulation object container, we have 3 objects, which is also in solution 1. And what you can do is you can right click and edit display. You can make them smaller, so it's a little bit easier to see which one is the top, which is the bottom. So now these 2 pieces are glued together. And next, that's all about the gluing. And next is the constraints. And a fixed constraint on the C-bar will not be sufficient for this model. Because, well, let's apply the fixed constraint first. Fixed constraint, that's very easy. Just pick the center node of the C-bar and say, okay, that's one constraint. And it will not prevent this vice grip from rotating along or around this C-bar. It's going to rotate like this, and it's going to go circular motion. Why? Because the fixed constraint can grab 1 through 6 on the C-bar, but it cannot transfer the 4 through 6 into your 3D solid. So your 3D solid now, it's just fixed on XYZ, but not XYZ rotation. Due to the lack of 4, 5, 6 in the 3D solids, then the whole thing can rotate. So what we can do is we can apply another constraint. So since this thing can rotate from this side, it will go up and down, which is the motion in Z direction. We can kill the Z direction any point on the model, really, except the C-bar. So I'll pick this one, and if you pick this one, it's gonna have the largest SPC force, which should be 0. So it doesn't matter. And picking this one up, you can actually examine how well your model is set up. If in F6 the SPC force is really small, that means your model is good. So I'm turning into a static wireframe. Then you can apply a user-defined. So here I pick the center node of the spider. It really doesn't matter. Maybe it's easier to pick the end point, end node, and the kill degree of freedom 3. Okay, which is Z direction, and okay. So this way, if you look from the side, you kill the Z, this point will not go up and down. So there's no rotation motion for the whole thing. So now the model is sufficiently supported. Then we just need load the forces for the model. So the idea of the loads are we squeeze at the very end point of those two handles, and also the two forces should be equal and opposite, and also on XY plane. So if you can't pick, or if you can't find which one is on the center or on the middle of your grip, especially this one's a little bit hard to see which node, you can turn off half of your handles. This one is actually the extruded, so you can turn off half, and for better viewing angle, I just turn off everything. So what you want is you want to pick this node. That's on the symmetry plane, by the way, and this node. You're gonna apply 10-pound force opposite to each other. So the force here, and magnitude is 10 pounds. The object, we can start from this side, pick this node, and the trick thing is the vector. So vector is determined by actually these 2 points where you apply the forces. So we're gonna define the vector using 2 points, and it's gonna pointing for this side. It's gonna be pointing from this node to this node. So remember, all the nodes now they're on the symmetry plane. And F8, you can take a look at the direction and apply. So we have the first force, then we have the second. It's the same 10 pound, and the opposite node here, and also opposite direction, the same point, and pointing to the other point. There's a force on that, and okay. So now if you look from the top, you can make them bigger, and see, edit display, make them larger, and they are pointing at each other, and they're equal and opposite, to make sure you can say information for the loads. Okay, once you right click on the information for the load, and you have 2 forces, and they're 10 pounds both, and look at the direction. That's the minus something, then this is positive, and the number matches. That means they are opposite, and that's a good check. Okay, so we have force, we have supports, and we glue those 2 pieces. This model is ready to run. However, for hand calculation or for the verification of our model, you want to know what forces are in the joints. Because if you look at, let's say, a single piece of a mesh, so if you look at this piece, and during hand calculation, you want to know what force is applied on this mesh for NX compared to your hand calculation. So how do you get force from NX on which force is applied on this mesh? The force is applied through the bushings, the SPs here. So you can actually ask for the output of those bushing forces and the moments. So what we do is we need to create an output group. So by default, that's the whole model, and we can right click and create a new group. And in this group, you have to, or you want to pick those 5 in this screenshot. So which 5? Actually, we need 4 of the bushings. That's all of the bushings. So 3 pin joints, 1, 2, 3, and 4. So 3 pin joints, 1 ball joint, and the last thing is the nylon bar. You can get axial force in the nylon bar from FO6. So that's the 5 meshes you want to have, and you can have more, but this is the ones you're gonna need it. You're gonna need it to do hand calculation. So okay, and there's output group. Okay, 5 meshes, and we can solve the model now. So first, again, you probably want to save everything. Then do a model setup check. And if you see something bad here, if you see error here, then you have to take care of that. So if you see something says the bushing have no coordinate system, then you have to go back to the FEM and right click on the mesh, edit mesh associated data, then modify that. Then if there's no material, you know what to do. So the warning is good, it's fine, it doesn't matter. And this iteration solver, that's also fine. You don't have to use that. So that all looks good here. Then you can just go solve. And remember, we have to enable the output group. So we have to edit the attributes, go to case control, and output request. Then that's here. First, you want to enable SPC force to print. Then you also want to enable the force. So this force is for the bushings. Then once you enable that and you want to change to print, that goes to FO6. Then here entity, you want to choose group, and the group is group 1 we just created here. That's the 5 meshes. And okay, and that's all we need. So I said okay and okay again. Now it's gonna run the model, and you will get results if everything's fine. It's very fast. Go to the results, and that's the result I have. And again, that's if you have results that's 10% within 10%, then that'll be good. That's acceptable. And also for the homework as well as the final report, you have to have your name here in the header. So we can right click here and edit this post view. Then here in the legend tab, you can change the header to customize. Customize it, then click here. You can add anything you want. So you need to add your name here. Then if you want to put an ID, that's fine. And say OK. Then apply. So once you apply, it'll add another line here. Okay. So that'll show this is your model and this is your result. Okay, so that concludes this video. Then let's see what we need. All right, then also remember we asked for the output request for the force for the bushings. You have to find your FO6 FO6 file. Use your text edit. Go to the bottom and then go up a little bit. should see this, the SPC force. Okay, we have two constraints, and you can tell this one is the second one because it only has some forces on the z direction, all 0 because we didn't constrain that, and this minus 11. So that's pretty good because ideally or theoretically your model has an opposite and equal force. You should have no SPC force. So minus 11, that's 0. Then this is your fully constrained, that's a fixed constraint. So that's all minus 5, minus 10, which is good. Okay. Then the force in the bar element, we only asked for one bar, which has two elements in that bar, the nylon bar. So you can look at the moment and the shear. What we want is the axial force. It's 13.48 pounds along the bar. So that tells you if you apply 10 pounds on the handles, you would get 13.4 pounds at the jaw, at the very tip. And that's not a very big magnification from 10 pounds to 13 pounds. It's less than 1.5 times. So, but if you look at the geometry, it's, the length from your force to the rotation center, then to the other side, it's pretty much the same. It's very close. So if you want to get bigger forces on the jaw, you should have a shorter needle nose on the jaw. Okay, then next is your bushings, and the bushings are the forces in your joints. Okay, and you don't know which one is which now. And I can tell you this one with 30 on the moments, that's the one on the screw. That's the ball joint. Why? Because we freed degree 4, 5, and 6. So you got 0. And let's see. And XY forces. Okay. All forces on Z is very small, which is good. That's out of plane. So all our forces is in XY plane. They should have nothing on the Z. Then okay, so this force is on the screw as well as on the link. So look at that number is 2.46, and look at the top. You have the same number. It's actually exactly the same number. The first one and the last one. And I bet you this top one is this pin joint. Why? Because later on you will know this link has only 2.0 force. It's a two force member, so it'll have opposite and equal forces on this piece. And here the sign is the same, but remember the bushing is only 1D, 1 point. There's no direction on that element, so the signs doesn't matter. If it's positive, that's fine. It's negative, it's fine. Okay, so now we determine the first and the bottom one is the 2SP on the link. Then the center 2 is the other 2 link. So those forces, that's the result from NX. Then later on you're gonna hand calculate. You're gonna find the force in that piece and compare that force to this result, and you would get, I think, within 2% or 5% of accuracy. Okay, so this is something you need to look at it. Okay, and yeah, this is the end of this video. Next week it's gonna be questions. There's no lecture, and we will post how to do the hand calculation on this project. And probably I'll post another video on how to measure the distance using the measure distance tool. And of course, we will give you the final results of the measurement. So if you don't want to do that, you can just use our measurement and you can do your hand calculation. Okay, that's all. Thank you.